Hello and Assalamualaikum warahmatullahi wabarakatuh. I am Haikal Yusaini from section 3 classes. Will present to you about the assignment for restraint beam. So in this assignment, figure 1 shows the part floor plan of the office building using the simple construction system. The floor uses in situ concrete slabs supported on restrained steel beam. The loading are given as follows, which is the permanent load is given 5 kN per meter squared, including the safe weight, and the variable load 4 kN per meter squared, and also been given the safe weight of brick wall on external beams and internal beam 3 kN per meter squared. So I will firstly present to you about the first question, which is to determine the maximum moment shear force and deflection experienced by beam DE, and design beam DE by doing all the necessary checking only once. So I will show you. In this question, we will find the design the beam DE. So the slab around it, we must calculate the how many way of the slab distributed the load. So we calculated here, we get 1 way slab. We calculated 1, 2, 3 slab here, we also get 1 way slab. So the only slab that distributed UDL to the beam DE is this slab. And then we also must calculate these two beams point maximum shear force to get the point load that was distributed in this slab. For the load calculation, we will find this using this formula 1235 GK plus 1.5 KK, which means this is dead load and this is live load. So 1.35 times the 5 kN that we get for permanent load, and 1.5 times 4 for the live load. So we will get 20.75 kN per meter square. So we also must find the load from the brick wall, because they is given that brick wall safe weight is 3 kN per meter square. So we will times with 4 meter, because we will find the brick wall at the first floor. The first floor height was 4 meters, so we multiply and we get 12 kN per meter. So we will get, this is the total load for the UDL1. So this load calculation that we get from the permanent and live load, we will times with 1 meter here, because this is 2 meter, we divide by 2, we will get 1 meter. So 12.75 times 1 meter plus this safe weight from the brick wall, and then we get the total UDL weight, UDL load is 24.75 kN. So like I said, we must find the secondary beam maximum shear to get the point load on the beam DE. So we just find the maximum shear here using the formula of UDL. So we will get 31.88 kN. After that, we will find the UDL1. So UDL1, we must find the maximum shear, maximum moment, and maximum deflection using the formula given on the deflection table. So we will get maximum shear 74.25, maximum moment for 5.5 kN, and maximum deflection is 417.66 over EI. After that, we will find the point load that we have calculated using the secondary beam shear force. So this is like what it looks like. So we must find the maximum shear, maximum moment, and maximum deflection for this point load. So we will get from the deflection table the point maximum shear 31.88, the maximum moment 63.76 kN, and the maximum deflection 244.41 over EI. And then we must total the maximum shear and maximum moment that we calculated using the UDL load and point load. So we will get the total maximum shear 106.13 kN, the total maximum moment 509.26 kN, and the total deflection maximum is 662.07/EI. After we get all the maximum moment and maximum shear, now it's time for design it. So first, I assume to use the 686 times 254 times 170 UKB steel type S27. So from the table 2.1, by using S275, I have checked the flange thickness and web thickness. Both are below 40, so I can use FY 275 Newton per millimeter square. Now it's time to classify the cross section that we have been chosen. So for the epsilon, I have used FY 275 Newton per millimeter square. So from the table, I can use 0.92 for the epsilon. So first, I will classify the web part. So from the web part, I find the D/TW is below 72 epsilon. So the web in class 1. So for the flange part, I have checked the C/TF is 4.45, which is below the 9 epsilon, 8.28. So the flange also in class 1. And then the cross section that I have shown is class time to check the maximum bending moment. So we will find the MCRD to check with the design, which is to check that our maximum moment is adequate for the section. So MCRD for class 1 is equal to MPLRD. So the equation for MPLRD is WPL times Fy over okay. So WPL we get from the table of dimension for the section that I have chosen. So we will get 1548.25 kN. So we have checked the maximum moment from the load. We divided with the MPLRD, and then we get 0.32, which is below 1.0. So the bending moment is passed. For the shear force resistance checking, we must find the design shear must below the VCRD. So for the class 1, the VCRD is equal to VPLRD. And then to find the VPLRD, the equation must have AV. So first we must find AV using this formula. And then after that, I find the AV is greater than this. So we will use this AV. And then for the VPLRD, just insert the AV from here to here. And then Fy using 275, and M0 is using 1. You must times 10 to the power of 3 to find the kilonewton. And then we will find the VPLRD 1486.1 kilonewton. And then the VED divided by VCRD, we get 0.07 is below 1. So the shear check is passed. After that, we must check the shear buckling resistance for web. So to check the shear resistance for web, we will find HW over TW must below the 72 times epsilon over notch. Okay, so we have get the HW over TW 44.5. So it is below 66.2. So there is no need to check for shear buckling resistance. After that, we check the combined bending and shear resistance. So we get the MED over MVRD just now, we get below 1.0, so pass. After that, we check the shear resistance. So we must find half of the VCRD, which is we get at 144.6 km is below the design shear. So there is no checking for combined bending shear resistance. Finally, it's time to check the serviceability check. So in this check, we find the vertical deflection checking. So the deflection max must be below the deflection allowed. For the deflection max, we have UDL load and point load. So we must find the both of these deflection using the deflection table for UDL and point load. So we total the deflection maximum, we get 0.96 mm. So we find the allowed. The allowed equation is L over 200. So the L for our beam is 6000 mm over 200 is equal to 30 mm. So absolutely our deflection is passed because the deflection max is 0.96 mm is below 30 mm. So we adopt the section 686 times 254 times 170 steel type S27 UKB for this steel design. Okay, for the question 2, if beam DE is unrestrained, what will you do differently from the above beam that you have designed? So I will not change the beam design from the above beam because I believe although it is unrestrained, it can support. So let's go to determine the buckling moment resistance MBRD is the beam is safe to use. Okay, for the case of unrestrained beam, we will find the MBRD to check for the unrestrained beam. So the parameter that have in the equation is reduction factor for lateral torsional buckling, WY, FY, and M1. So first we must find the MCR because the MCR was the parameter to find the lambda LT. Okay, so we first must find the C1. For the C1 factor, we will use the UDL load because our load was beam was unrestrained to the slab that distributed UDL load. So we use the C1 factor 1.13. that we will point 1.132 for the C1. We must put all the variables such as E, IZ, LCR, and IW. So E and IZ and IW, we get it from the table of dimension. So for the LCR, we must find the critical length. So the critical length is have factor of K 1.0 because both of the end support was free. So we will get 6000 mm. So just put it all the variable in this equation, and then we get the MCR is 1961.68 kN. That it's time to find the lambda for the lateral torsional buckling. So in this equation, we get MCR from the before equation, and then we just put it in this equation, and then we will get the lambda LT 0.89. We must find the imperfection factor. We don't use the lateral torsional buckling curve to find the imperfection factor because the question didn't given the reduction factor. So we will use table 4.5. So first we must find the H over B, which is height of beam, and B is 2.7088. So it is greater than 2. Now take a look at the table 4.5. We use roll I section. So the H over B is greater than 2. So we will use the buckling curve B. For the imperfection factor, we will use B 0.34. It's time to find the phi LT. the VLT was must find because we will use the reduction factor of lateral torsional buckling. We have phi lateral torsional here. So first we must find the VLT. So this is the formula. So we just use we have find the imperfection factor and the lambda lateral buckling here. So we will get 1.06. So in the reduction factor of lateral torsional buckling, we just put the VLT that we have got here, and then we will get 0.61, which is below 1.0. So the reduction factor is okay to be used. And then after that, we use the MBRD formula, just put it the reduction factor that we have got, and then we will find 944.43 kN/meter. So our MBRD is greater than the maximum moment that we have been designed. So for the unrestrained beam, it is safe to be used using the same section of the restrained beam that we have been designed before that. Okay, lastly, if the office is designed not based on the simple construction, for example continuous construction, what would you do differently from the above beam that you have designed? So basically, like I said, I will not change the beam design that I've been checked just before this, because in the continuous construction, we must put the beam continuously, so we didn't use bracing, and then the work will be fastly done. So I will stick to my beam design just before this. So I will put it all the beam using the same design. So that's all. Thank you.